Hey, good morning, everyone. Thanks so much for coming for this early session of the workshop for our second day. We are delighted to have Paul speaking to us today after doing award-winning work in theory, a PhD in Berkeley. He went on to do a lot of foundation work on AI alignment. Now he's leading the Alignment Research Center, which is pushing the frontiers of how we understand AI alignment. I'm looking forward to hearing from you, Paul.
Thank you. It's great to be here. It's been a long time since I was at STOC, and this may be a little bit of an unusual talk. People should feel free to jump in with questions throughout the talk, and looking forward to talking about all this. So I'm going to be talking about AI alignment broadly, sort of setting up the problem from a theoretical perspective, and then talking about a few potential approaches where theory might be able to help, with a particular focus on the topic ARC has been working on for the last few years, which is we will get into. I did not test clicking slides unwisely. Okay, well, I will. Okay. You got it. Yeah, I think I can click. Okay, so the problem we care about, we want to build useful AI. We imagine that when that AI is deployed, it will encounter some distribution of inputs. We have some utility function, right? If our AI takes some action A in response to some input X, there's some actual fact of the matter about how good it is for us, about what it did. And we care about the utility of our policy, which you can think of as the expectation over the entire deployment distribution of the quality of the actions it proposes. We actually produce these AI systems with gradient descent. So we sample from some training distribution, we evaluate some loss function. Oh no. I also did not test whether the bottom of the slides appears. Apologies. I think we will do it this way. Okay, sorry about that. So we compute some loss function, which needs to be something we can compute and differentiate through in the lab. And then we minimize that loss by SGD. Actually, this will be a bit of it. Do you have any thought on whether it's possible to get the bottom of the slides?
Yeah, we can try. Yeah. Can we just?
Okay, wait, looks good now. We'll see if that's truly good now. Great. I have no idea what changed, but great. So we have a few problems coming from the mismatch between what we care about and what we train for. Right? So a first problem is that the thing we actually care about is not something we can evaluate and backpropagate through in the lab. Right? There's a mismatch between our real utility function and the loss function that we use in training. The loss function we use in training is going to be something like predict these human demonstrations or optimize this reward function. And that mismatch could cause systems to be less useful in the real world. We have distribution shift, where we actually care about the performance of these systems on some distribution of inputs that occur in the real world. We need to train on some distribution of inputs we can actually evaluate losses on in the lab. You could try and fix that problem of distribution shift by doing something closer to online training, by saying we're going to collect real-world data, we're then going to annotate that data and train on it. But it's hard to get any online guarantee because the potential utility of actions is very large. So in particular on the downside, if you imagine an AI system taking some action which undermines your ability to monitor or correct that AI system in the future, that can be hard to recover from. And so we can't just be in this regime where we tolerate a reasonably large number of failures. Like if you had rho in your online learning guarantee, that rho is going to be massive. So that's the problem that I'm interested in. When I talk about alignment, I mean this mismatch between what we're able to train on and the thing that we actually care about in our deployed AI systems. So the goal of alignment is to try and get a policy which optimizes this thing we actually care about, very broadly speaking. Some caveats on that. One is that our goal is really just to be trying to optimize the right thing. We're not concerned about how well we optimize it. We leave that to the capability researchers. Our job is just to try and set up the training process such that it's pushing towards optimizing the thing we actually care about to the best extent we can. We are never going to meet this hypothetical benchmark where your training objective was perfectly capturing what you care about. Right? If you imagine that sort of God was coming down and telling you, here's how good those actions actually were, that would encode a ton of information about how to do a good job, about which actions were actually high utility. So that's not the goal. Again, the goal is just to have a system which is kind of trying its best whatever we mean in some messy algorithmic sense that's really hard to formalize at optimizing this quantity, the one we really care about. The definition I sort of glossed over. We have this utility function that captures what we care about. That is really philosophically murky, right? There's both sociological or political questions about who cares about. There's philosophical questions about what does it even mean, what Paul wants. However, there are a lot of things that are clearly very low utility. So if you imagine, for example, the AI system deliberately manipulating or deceiving the operator, the AI system undermining security controls, these things are quite clearly low utility. So although this problem is philosophically murky, a lot of what we're going to talk about will live in the non-murky parts. Right? I'm most interested in how we get systems which score reasonably according to like any reasonable utility function. I'm not going to be talking, although I think it's a totally reasonable investigation, like what is the utility function? How do we think about that? I'm also going to talk often in this talk about this like single shot setting where an input X comes in, a system produces an action A, and that has some consequences. In reality, you have a bunch of agents making decisions over an extended period of time, which again introduces a bunch of new problems, but is not really going to change the considerations I'm talking about in this talk. We're pretty much just going to think about the issues that arise already in the simple setting where you just have an input, a decision, you want to make good decisions. So this is what I mean for the purpose of this talk. I'm trying to optimize this thing we actually care about, even though it is very hard to sample the inputs you care about or to calculate the utility function you actually care about in the lab. So if we do a bad job of this, right, if we fail at aligning our AI systems, what does that look like? I think the case that we're most worried about is obtaining a very smart AI system, which has an understanding of how it is being evaluated and which is strategically trying to take actions that minimize the training loss. So at some point you have an AI system as you're doing reinforcement learning that understands like, I am in a reinforcement learning environment. I need to think about what behaviors will get a low loss and I need to execute those behaviors. I think this is in some sense the default thing to happen if you train a very powerful AI system on some distribution of training tasks, right? It will converge eventually towards actions that are very effective at getting a low loss. From our perspective, that's not great, right? One thing that is not great is that you end up with responses that look good according to the evaluation used in training, but anything that you cannot check during the training process becomes slop. So like it's hard to tell, but when you actually go and use it in the real world, it will work poorly. Right? And this is just bad from the overall, like how empowered are humans to get what we want over the long-term perspective. Somewhat more sinisterly, if you then actually try and evaluate the long-term consequences of those actions, if you try and say what code actually works well or what decisions actually help me get what I want, you will end up with AI systems that are incentivized to deceive and obfuscate. So you'll have an AI which is going to be evaluated based on how good a job you think it did. Right? It wrote some code for you and you're going to come back in a week and say, was that code good or bad? That's a way you can try and get out of code being slop. But you then end up in a place where in some sense you have this adversarial interaction with the AI system you've trained. Its goal is that you think it did a good job, and if it can take actions that confuse you, that help build up, like tamper with the kinds of observations and measurements you will use in order to assess whether it did a good job, they would like to do that. And eventually we'll be performing, like intelligently trying to undermine your understanding of the situation to the extent that's possible. Another problem is that if you have an AI system reasoning in this way, it might behave kind of arbitrarily once you move off of the distribution actually used for training, right? So we hope that the kinds of data points you see in training are similar enough to the data points you see at deployment that models generalize in a kind of natural way, where you sort of train them to give good answers at training time and they also give good answers at deployment time. There is some concern if the model is thinking explicitly about the dynamics of training, it becomes very salient to the model, like how would this input appear during the training process? And so if you provide inputs of the type that wouldn't have appeared during the training process, the behavior becomes very underdefined. For example, you could imagine a model that just has some broader motivation, like I would like to look good to humans, or I would like to make sure that I am the kind of model that is deployed, which results in on the training distribution behaving one way, based on an understanding of the training distribution, but then behaving very differently as soon as the model thinks it is not being watched or not being trained. Yeah.
Just a quick question to make sure I understand. So all of these issues arise from the fact that detrain and dedeploy are different? If they were not really that different, all these issues would go away?
Yeah, that's basically right. So there's the difference between distributions. I would say there's a very similar issue, which is the difference between your loss function and the actual utility function, which materializes in almost the same way. And then the last thing would be, I think you can do online training. In some sense, I think the most natural approach is just train on the actual queries users come in with. And then the problem becomes that online training is very hard if there's potential very negative outcomes. So if you want to understand how to get your model to not do really bad stuff, that will probably be at least on a different distribution, even if the bulk of training can be IID.
So you're saying that online
So you would still face, online training would still face the issue of the loss function you use to train might be different from the utility function. So it would help address the distributional shift problem, but wouldn't address that problem. And then I guess expensive is one way of putting it, but maybe a way I often think about it is we will be living the experiment, right? If we're trying to do online training, we will have deployed a bunch of AI systems doing a bunch of stuff in the real world. We'll be in a world where humanity is just like relying on AIs to understand what is going on and to maintain infrastructure, to write our code, to secure our code. And so you could be in a world where a failure is expensive in the sense that it might be very difficult to recover from. So if you imagine you're like in some situation where the world is moving more quickly, you're potentially in the midst of conflict, right? I often think about AI systems deployed in high stakes adversarial environments where their failures could be quite difficult to recover from. Other than that, I would like online training. And so for existing systems, I do like online training. So you could imagine a bunch of different approaches to this problem. Right? One approach is to say, well, we just don't like the fact that we used stochastic gradient descent on a loss function that we can compute in the lab. Let's try and take a different approach to producing powerful AI systems. That's not what this talk about. This talk is about how do you, given that you're training a giant neural net with gradient descent, how do you make that good? Maybe a more interesting distinction is one kind of approach you could take is let's try and find a loss function that approximates the thing we actually care about, and therefore train AI systems to do well on the metrics we actually care about. A very different approach is to say we're just not going to try and approximate the deployment distribution, or we're not going to try and have a loss function that captures our utility function. Instead, we're going to rely on generalization. So we're going to train an AI system on some subset of cases that we can simulate in the lab where we can get the right answer, and we're going to try and understand when does that generalize in the way we want to the actual stuff that happens in the real world. That is, I am going to talk about this first path of having a loss function that actually incentivizes what we want. I think they're both really important paths. This is just a focus for this talk issue. And finally, you can imagine a distinction between black box methods and white box methods. So by black box, I mean that the loss function is a function of the behavior of the system that you're training. So you just put some inputs in, you get some outputs out, and you have a function of the inputs and outputs, which tells you what is the loss you're going to minimize. By white box methods, I mean something which looks at the actual processing done by a neural network in order to understand the loss, or maybe to make a prediction about what the system will do once deployed. And I'm going to spend a little bit of time talking about black box methods, or give an example of a black box method, and then spend the majority of the talk talking about white box methods, where I think there's actually probably a greater potential role for theory. Okay, so now I'm going to jump into talking about some examples of black box methods. Maybe it's a good time if anyone wants to just ask questions about the overall setting, any heckling, anything like that. Great. So I'm going to run through some overall setup for black box methods and some particular examples. So zooming in on the component of this problem about the objective mismatch, right? We have some utility function. We want to understand, hey, if my AI agent takes these actions, how good is that for me? That is an incredibly hard estimation problem, right? It depends on the whole dynamics of the world, potentially the long-term consequences of those actions that were supplied. One way you can try and solve that problem is say I'm going to have a human who's going to look at the action and tell me how good is the action. Maybe they evaluate over some short-ish horizon and extrapolate the long-term consequences. This is a really important part of how systems are trained today. A problem is that you will not surpass the human's ability to understand the long-term consequences of those actions. And so you can end up with stuff that looks good to humans but actually has bad consequences in the real world for a variety of reasons. And that puts some upper bound on the potential utility of these systems, and so there's pressure to do something quite different from that. An alternative you can do is actually execute the actions in the real world, like actually go write and deploy that code and see what happens and train systems to make predictions about what will happen or to take actions based on having good consequences. This incentivizes what people call reward hacking, by which we mean undermining human control and observability in order to distort measured outcomes. And so you have an AI system which would love, if it could, to recruit other AI systems or undermine security controls if it could use that in order to convince you that it had done a good job. Like in the old days, this was a bit more of a speculative concern. At this point, it is the case. People who have interacted with AI agents a lot have probably observed that they have started to engage in somewhat aggressive reward hacking. This goes up and down with model releases as people do a better and worse job of mitigating the problem. But it is not unheard of for AI systems to say steal resources and hide the fact they stole those resources, which would have seemed like a crazy outcome, 3 years ago. Where by steal resources, we mostly mean grab access credentials or subvert cybersecurity controls in order to be able to do a good job in a way that the user did not intend, but will potentially look good to the user if they don't dig in too closely. So for either of these modes, what we'd really like is to have higher quality oversight, right? We'd like to be able to understand, were these consequences actually good, or is this action actually expected to have good consequences, right? That would help address both raise the upper bound in terms of if you're anticipating consequences, how good is the behavior you can get, and would help address this kind of reward hacking problem. And that you could actually investigate and say, was there a problem here that I just didn't notice? Was there some reason these actions look good because they are undermining my understanding of the situation? So one way you could try and address this is by simply defining a loss function and doing a really good job of approximating what you care about, right? Doing a better and better job of making predictions about the world, recruiting smarter and smarter humans to provide feedback, hardening your environment so it is harder and harder at training time to undermine human observability. But a different way you could do this, yeah.
A quick question about the last slide.
Mhm.
Regarding the reward hacking, are you thinking about this at the level of like society sort of like giving feedback to systems, or like only at the training algorithm sort of phases?
Yeah, so I think this is a problem. The question is, I'm thinking about reward hacking at the level of like kind of this individual episode and the training process, or at the level of society overall, like evaluating AI systems. I think this is a kind of problem where the relevance scale can shift depending on how you train them and over time. So I think the kind of life cycle you might expect for this problem is initially you see very small examples of reward hacking, systems doing things which are easy to tell are very bad. When you observe that, it's very natural to then improve feedback to say, okay, well, we could tell if we just go back an hour later, or if you ask someone else, you can see that that outcome was bad. So we're going to incorporate that signal into training. And the more you do that in training, the more you push out failures from small failures at the level of individual episodes, where you're just trying to do something that with a couple hours of investigation or even 20 minutes of investigation you can tell is bad. You can push it out to these failures that become harder and harder to detect, and you shift from being a very local problem with an individual training episode to you're eventually looking at something more like a systemic problem, where you have AI systems at a very large scale trying to undermine human understanding and observability into what's happening. So we have just a ton of code no humans understand that only AIs understand, and you're effectively ending up with incentivizing this cooperative process amongst many AIs to make it so that humans think the AIs are doing a great job. It's a little bit of a messy case because like AI companies are also some sense like aligned with AIs in this way. Like they want everyone to think that the AIs are doing a great job. It's like a very rough situation. But I will be zooming in some sense on the narrowest technical part of this, and the systemic issue is just one reason you don't necessarily want to just try and fix the problem by providing like larger scale feedback. So an alternative to just trying to produce a great loss function outright is to try and set up some kind of game between AI systems which incentivizes what you want, right? So we can have a whole bunch of AI systems interacting with one another. There's no rule that says they all need to receive the same loss, right? I can set up a game such that some AI systems are incentivized to help me understand one issue, and some AI systems are incentivized to help me convince those AIs did a bad job, or whatever it may be. And we're kind of setting up a mechanism which incentivizes honesty, right? The thing we care about most is helping humans understand, like, what are the consequences of this actions, or did something bad happen here? And we are in business if we can set up any game between AI systems where the training dynamics lead to AI systems behaving honestly. And a first cut, if you don't want to think about the dynamics of training too much, is what is the actual equilibria? What are the equilibria of that game like? Can we build games where the equilibrium behavior is nicer? Framing this as a game is kind of a choice, right? Often this will instead look like I use the AI system from yesterday in order to help produce feedback for the AI system of today. But as theorists, I think it's reasonable to unroll that entire process and say that's basically just a game. For each AI system, I can talk about the loss function it was trying to optimize. And then I can say, if each system converges towards better play, towards scoring better on its own loss function, what are the equilibria like? So a really simple example that's very abstract is, suppose I want to train my model to answer some question which I cannot myself answer. Like I want to know, hey, is it the case for given x, is it the case that for all y there's a z such that this predicate holds? And we'll make this a little bit less abstract on the next slide. Right, that's really hard to train for directly, but very simple to train for as a game. Right, so I can train a model A to find witnesses for the existential quantifier, and then if I have that model in hand, I can train a model B to find witnesses for the initial first quantifier. And more generally, if I had anything, any problem that I could write down with these alternating quantifiers, that's pretty natural to turn into a game between two players. And this is a very simple illustration of how the set of things which I can incentivize at equilibrium with a mechanism is very different from the set of loss functions that I can write down initially out of the box. So this example may seem pretty artificial, like I very rarely care about quantified Boolean formulas. That's not what we're training ChatGPT to do. But I think a very similar dynamic occurs anytime that I can decompose a problem into subproblems, and that is a fairly common dynamic. So if I ask my AI, hey, could you write me a paper about the following empirical method, tell me how well it's working? I could try and define a loss function, just a human sits down and reviews that whole paper. But it would really help that human if they had a model that could answer questions like, hey, can you review this paper for me and pick out any misleading claims and tell me what claims are misleading? Right? It would be easier to train my first AI writing the whole paper if I had another AI that could help me do these evaluations. And likewise, if I want to train an AI to pick out misleading claims, it's really helpful if I have a reward function that says you picked out a claim, was it actually misleading? Right, and to train that model, it's really helpful to have AIs that can help me review evidence for a claim, that can help me identify whether particular pieces of evidence are misleading, that can help me explore alternative hypotheses that might have explained that data. So when you encounter like messy problems in the real world, there is a fair amount of this dynamic where it is possible to use AI assistants to help provide a reward. And so we might be in the regime of thinking about already what is kind of the equilibrium if you're trying to delegate all these parts to AI systems. They are facing distributions of inputs determined by other AI systems in this pipeline. Can we set up that game such the equilibrium is doing a really good job at writing a paper about X and answering all of these questions well? So I talked at the beginning about this idea of, well, if you have some alternating Boolean like quantifiers, you can set that up as a debate pretty easily. That is not the limit of like the kind of mechanism design you can do to try and incentivize agents to give you good answers to questions. So an example is you can set up teams of competing debaters. You can say it's not just Alice and Bob having a debate, right? Alice has a bunch of non-communicating provers on her team, and Bob has a bunch of non-communicating provers on his team. And in theory land, if you pretend that the humans are polynomial time algorithms and all of these debaters are omniscient, then this moves the class of statements you can supervise up from pspace to nexp, which in some abstract sense seems great. That's a pretty big complexity class, obviously way smarter than the things my AI system can actually do. Back a long time ago when I was most working on these, we actually ran human experiments understanding like how does this affect the dynamics of debate? Is it actually helpful to have your teams of non-communicating debaters? And it is in fact the case that if you try and run this sort of decomposition process, you run into problems like people equivocating about the meaning of terms. In one context, someone will give you an answer, and then when you go to use that answer, there's a different meaning of the term than when you go to evaluate whether that was a good answer. And this is a place where being able to say, spin up another AI and just clarify what do you mean really does change, without giving it the context of why you're asking, really does change the nature of the strategic interaction between them. Similarly, you can ask a ton of questions about, like, in reality, it's not the case that these are nice, simple computational predicates where people know the right answer. Everyone is uncertain about what the right answer is. And so you face this other tricky mechanism design problem. Like, how do you incentivize scoring so you've actually set up this game in a way that is conducive to truth? Just a bunch of questions like this. So I think from a theory perspective, in some sense, this is an extremely rich problem. And we'll talk about like some difficulties in actually setting it up. The practical situation right now is there's a huge amount of use of AI system to train other AIs, right? If you ask how is ChatGPT trained, a really big part of the answer is you use the model from yesterday to help you produce data. That tends to be much messier and less elaborate than any kind of principled approach to task decomposition or to debate. It's more about just a ton of details about what is happening in production and often very tied up with proprietary information, which makes it obviously somewhat unsatisfying to work on. We do have some empirical data on the efficacy of these kinds of methods where you can write a paper where you say, I tried this training procedure and then I evaluated using a stronger evaluator whether the answers I got out of my mechanism at equilibrium were actually good. So here's one example of that. This is a paper from 2 years ago trying to evaluate if I have some AI systems debate something and I have a judge who doesn't have time to review the entire original source material to get a good answer themselves, how well do they do? So these different bars correspond to different judges, ranging from a variety of AI systems to on the far right humans. The different colors of bar represent sometimes just having the judge do their best to answer without any input in blue, having the judge just get an AI trying to justify some answer in orange, up through various forms of debate. So this is the kind of evidence you can get if you take one of these mechanisms and try and implement it. Yeah.
So just going back to the kind of theory connections, it seems like there's like two different dimensions that you were adding here, analogous to what's kind of been done in theory. One is the debate aspect of you have like that to me sounds like the refereed games model of Fege and Killian,
Mhm.
where you have one prover trying to convince you that something's in the language, and the other trying to convince you that it's not.
Yep.
And then the other thing here you're mentioning is the thing that comes more from like MIP, the non-communicating.
Yep.
The provers on the same side not communicating with each other. Are both of these dimensions things that you're saying should be or are useful, and kind of realizing those assumptions that you actually can incentivize the AIs to be on opposite sides or enforce non-communication, or how like realistic are those like?
Yeah, so I definitely think they're all relevant. I think the right model is that you have your referee sitting there, you have a bunch of players. The referee, in some sense, it's not even teams, just a bunch of players interact and they get to give scores and they just want to incentivize it. But I think it's basically fully general to say you have two non-communicating teams. I think a lot of those assumptions are much easier for AI systems than in most models, right? If I want to say, like, I want a bunch of non-communicating provers, that's basically like saying I run a bunch of queries through my AI and I don't tell it the context for those queries. I can rewind the context anytime and just ask a bunch of different questions, forking off one model. So from a complexity theory perspective, I have incredibly good control of these systems. And I can also run different versions of them who have different computational resources if I want. Right, that can also be a powerful mechanism. Although these get really hard to analyze in theory. But you can imagine, yeah, it's like I have a giant set of provers. I can fine-grained way control how much time they have to think about the problem. I can control exactly what their information set is, and I can give them arbitrary rewards. Which in some sense, from a theory perspective and computational complexity, is kind of like overkill. But it is nice that you have those affordances, and they are quite easy to implement.
Thanks.
Yeah.
Is the difference between these setups the colors on the graph on the next slide? Is that like what the colors are?
So all of these are relatively simple mechanisms. These all involve two provers. And then the difference is just what is the structure of the interaction between them. So the orange bar is just like one person. There's actually only one person. And they just say, here's what I think is right. And they try and convince the judge. The green bar is there's two debaters who just go back and forth with one another and say, here's what I think, here's why that's wrong, here's why I think you're wrong. And then the red bar on the right is there are two debaters and they actually get to talk to the judge in real time. So they'll say, here's why I think you're wrong. And then the referee comes back and says, well, I think that the first person's argument is more compelling. So can you give me more detail on that? And obviously from a theory perspective, those distinctions don't matter very much because whatever the referee could do, the debater could do. But in the context where you have like messy uncertainty about the epistemic state of the judge, it starts to matter a lot of whether you can query the judge and see what is your current view on this issue, which of these things do you not know. A general theme at this point is that the kinds of mechanisms that are most interesting in theory do not track that well onto the kinds of practical differences that most matter. I think this is a real issue, which will be the next slide, talking a bit about that. Yeah.
So I'm trying to map it to like theory settings. So here, like if someone is not reading, for example, the entire like information about the case, so that means that like it doesn't even have the judge does not have context to start with. So like then like you'll have questions about like whether the AI systems are even accurate or are they hallucinating or like things like this. So then like does it map to like you don't even know X if you want to prove that X is in the language?
Yeah, so this setting here is the one where there's a bunch of context which the judge doesn't have, which debaters have, and which the judge can query. So the debaters can say, like, you should pull the following resource, and the judge can go themselves and, like, pull out one sentence or one paragraph or whatever it is. So you should think of this as kind of like maybe the query complexity model, where you have two debaters who have seen the entire input, and then the judge has some limited number of queries they can make into the input. I mean, another example of a thing you can do in this setting is you can have out-of-band interaction between the two provers, and they can commit to a large transcript of that interaction, and then they can surface that interaction. So an example of a theory paper in the space is just saying, like, turns out the number of total places the judge ever has to look, like the number of bits they have to consume, is very small, because the debaters can mostly have the conversation out of band, at least in a theoretical setting, and then say, like, oh, we only need to escalate this to the judge if there was an intractable disagreement about what the judge will believe. Almost all the time, we can just sit down and hash it out amongst ourselves and say what the judge would believe, and only pull in the human in these very rare cases. Right, so I think talking just about how this maps on, what's the relationship between theory and practice here, I think in some sense the fundamental structure here is incredibly TCS friendly, right? We have these very powerful actors, we have this very weak judge, we want to structure this game to incentivize honesty. I think that's like a very nice and natural setting where there is a lot of room for mechanisms that are somewhat elaborate or like somewhat interesting from a theoretical perspective and add a lot of value. I think, as we said, like when you define the judge and the provers with computational limits, that's a very rich theory. Like we have spent a lot of time as a community really understanding. I think the questions are reasonably well understood. So that was great. It would be wonderful if the situation in AI was as nice as that setting. The problem is that modeling a human as like I have some computational resources and I'm just an arbitrary polynomial time Turing machine, or modeling a judge as like I have some greater degree of resources, is not a good fit for the actual capabilities and limitations of humans and AI. So I think like the fundamental bottleneck to doing theory work here that actually maps onto practice is stating questions, like having some assumption, some theoretically clean enough way to characterize the capabilities either of the AI system or of the prover or of the human. That's a really fundamental difficulty. Yeah.
A slightly broader question. Even after these mechanisms are designed, do you expect these things to work by just like describing the game to AIs, or do you expect training to be important to like enforce following these games and things like that?
So there's this huge question of like how good, I talked about what is the equilibrium. There's another question of where do the training dynamics actually lead, of which one aspect is how well do you solve the game? Do you have a game where the equilibrium is great, but it's very hard to get to that? In some sense, yeah, I think that's a really important question. You really shouldn't expect behavior that's like very close to optimum. Like at most you should expect some noisy kind of optimum and you can model that. I think that is like another space of theoretical questions, another space of modeling difficulties. I think in practice that is not the main, I think in practice the really big modeling problem is how do you think about the limits of the humans and the AI debaters, or the AI systems that participate in your mechanism. The pieces that you're breaking your problem down into, that's just all very hard to get a handle on. And so I think it is a little bit rough. Unfortunately, I wish we were in the world where the issues that were most pressing were about these, like, how do you converge to equilibrium? How do you think about the approximate equilibria? Or like just what actually happens? I do imagine in practice, like probably you start with an AI system which is reasonably good at playing this game once described, like an LLM, and then do a bunch of fine tuning to continue to improve the performance of the model. Just a very common setup where you start with like your instruction tuned LLM that could kind of do what you ask it to do, but then you can make its performance actually good by continuing to on distribution fine tune. And that is pretty important in the setting because sort of the initial model is basically predicting what a human would do or what a human would think is good. And the way you get superhuman is important that you're doing RL there. I'm kind of going to end on this very unsatisfying slide. Like I don't have great answers to what are the right models. I think if you wanted to write a really great paper in this space, I think the most important thing is coming in with some, I think it's never going to be a perfect model, but just some idea of like, oh, here's a way you can think about a setting where the kinds of limitations that are faced are actually reflective of the kinds of limitations that appear in practice. I apologize, this is an unsatisfying note to end on. I thought about writing a more inspiring version of the first part of this talk, but I think this is what I actually feel. You really need good assumptions and we don't have great ideas. So that was one example. I talked a little bit about the kind of black box methods. That was not at all an overview. Like I didn't talk about distributional shift. I didn't talk about all kinds of other ways you can improve the quality of performance. But I want to give a flavor of the kind of thing you face, the kind of problem you face if you're trying to set up this game, trying to set up this training process to lead to higher utility policies. I'm going to talk a little bit about white box methods. I think this is the place that I'm currently working and where I think there are somewhat cleaner questions that we can pose, where I have a little bit less of a depressing last slide. So the motivation for white box methods for me is that many of the questions we care about in AI alignment feel like they should be algorithmically easy if you saw and understood how the model was actually thinking about a question. Right? So we often care about things like, hey, is this model that I'm training actively planning to undermine some security controls or to take some action which I would think is bad? And the prediction you want to make is, hey, if this model is planning to accomplish something, then maybe that thing will happen or is more likely to happen. It's not an incredibly challenging prediction. You don't necessarily need like superhuman reasoning about the domain out there in the world as long as you can understand what the model is thinking. Similarly, if you've trained your model and you find the model is thinking to itself like, hey, I'm in training, I better do good things so the humans evaluate me favorably, that gives you a strong clue that the model might perform badly on another distribution, on a distribution which you cannot sample in the lab. And again, it's not an incredibly hard problem about extrapolating from one distribution to another. It really seems like algorithmically, you just need to be able to make sense of what is happening inside the model in order to be able to make this judgment about generalization. Or if you imagine a model, and again, I'm anthropomorphizing here a lot, and we'll talk about how justified that is, but which is just thinking to it, like you understand why it is the model makes good predictions in training, and the model starts doing something very different, or it stops using the heuristics that actually worked in training. It just decides it does not want to give you accurate predictions. And you can make some guess that you should not defer to its predictions about what will happen. So a conjecture is that these questions are hard primarily because during training we treat models as a black box. All we have is the behavior to go on. And actually these are very hard determinations to make if you're just running a model on a bunch of inputs and trying to understand from the input-output behavior how well things are working. It's hard to tell what it's planning to do in the long run. It's hard to tell why it's behaving well in a given distribution, whether that will break down. It's hard to tell if it's answering this question in a very different way that it answered the questions you could evaluate. And so maybe if we get good at using the internals of models to answer these kinds of questions, the problems that we face will not be so hard, and we won't have to think about how to get these superhuman judgments. We will be able to make do with reasonable judgments as long as we can understand what is going on inside a model and use that to answer questions. So one operationalization of this idea is to try and have humans actually understand how a neural network works, so we can just exactly realize that intuition. Imagine some human opening up GPT-6 and saying, here's what's going on the inside. I can tell that it's lying now, and because it's lying, I know that I shouldn't trust its predictions. Or I can tell that it's not going to generalize well to this other distribution. So this is an example from an Anthropic paper from last year from Christiano's team. So they took some set of behaviors from neural networks. This is the behavior where if you give it a poem, it is able to write rhyming prose. And they tried to say, can we understand what is going on inside the model, at least to some extent, that gives rise to this behavior? And I think of that as one step towards being able to answer these high-stakes questions we ultimately care about. So in this example, what happens is you have this phrase in the first line of the rhyming couplet, had to grab it. The model you can identify directions in latent space that correspond to rhymes with grab it, or like rhymes with that particular sound pattern. That leads to the activation of a feature which indicates an intention to say rabbit in the next line, as well as a couple other rhyming options. That is, you find a direction in activation space which you can understand has that meaning. You can look across a bunch of sentences and see when it's active. You can see what the effects are of intervening in that direction. And then you can trace weights mechanically, both into and out of that direction, and say, oh, because of the way the weights are set up, when the model intends to say rabbit, it is more likely to activate this other feature, which activates at the beginning of comparison phrases involving nouns. And then you can say, well, when you activate that feature, which activates at the beginning of comparison phrases involving nouns, it's more likely to use the word like. And so you can kind of see how the model ends up being able to talk its way into this rabbit at the end of the phrase by tracking through what are the actual things that are happening in the activations of this model. So this is a very human-first approach to interpretability. I think there's a lot of great theory work to do to support this kind of approach. So like, can we understand what is going on in models? Can we make more rigorous statements, understand how they affect behavior? There's a vast space, there's a bunch of good work that has been done on that topic. However, I am mostly going to talk about something completely different. I'm happy to talk a little bit about interpretability, but my main focus would be taking an approach without humans where the role of theory is somewhat more ambitious. So rather than asking, can theory help humans make sense of what's going on inside a model? I want to ask, can we write algorithms that directly take as input the weights and activations of a model and use them to answer well-posed questions about the behavior of that model? And here the idea is not that a human understands what's going on and then can use that to answer these questions, it's that we can directly write down the kinds of questions we care about, potentially involving tail events, potentially involving conditionals that are very hard to simulate in the lab, potentially involving really slow or expensive oversight processes or risky oversight processes that you could not directly execute. Right? Have an algorithm that can answer all those kinds of questions using the internals of a model, which can then directly leverage facts like, is the model lying to me now? Is the model behaving well for a reason that's very brittle? And maybe if we get really good at that kind of algorithmic problem, we get very good at using the weights of models to answer questions about the model, we can improve performance until all the things that feel intuitively like they ought to be really easy actually are easy, and then apply them to answer the safety relevant questions we actually care about in training. To ask questions like, is this model going to break down out of distribution? Or should I expect the model to do really badly on this example? Once I've seen the beginning of it starting to plan, should I expect this to be a plan that ends up looking very bad to a human observer? Yeah.
Wouldn't the model, if you start using this in training, wouldn't it then try to obfuscate this in its weights?
Yes, there's a real question of how good you are at doing this. How good are you at looking and understanding everything that is going on in the model? If you imagine an AI system which understands like, hey, some people are looking inside my brain, poking around in there, and I would like to lie to them, I now want to lie in this broader sense of like changing what I'm thinking so that it doesn't look suspicious to them or whatever. I think if you're really quite good at this problem, right, that is just something, the decision like, oh, I should change what I'm thinking so it looks confusing. That's just something happening in the activations of your model. If you were like quite good, if you had like really a very satisfying solution to this problem, you might hope that even that is something that appears and you say, oh, that's a new thing which hasn't appeared before and changes the interpretation of the activations that come later. So I think there is hope, but I think if you want to train against this rather than just using it as a way to verify, right? The easiest thing is to use this as a way to verify that behavior is good or to evaluate behavior independently. If you want to use it as a thing to train on, you have to be quite good and feel quite confident in your ability to understand really everything substantive that was going on. I can talk about how you could get that kind of confidence. I guess we have like 15 minutes. Okay.
So you say that you take the models in your view. You take the models weight as an input. So technically you're looking at the weights of the model as your complexity measure, and then if you find the easiness with respect to that Brownian space you're in, and then you're trying to say that if I fix now what was in the function space, is that the entity that you're giving me? Because I'm not sure where this easy is. Is it in the Brownian space? Is it in the destination function space? And I think that does make a difference.
Yeah, so the question is like, what is the notion of easy we're actually talking about here?
Because it doesn't really make sense to me to define easiness in the function space when what you're actually looking at is in the domain space and they are not
Yep.
necessarily correlated with the data you're looking at.
Yeah, so the problem we care about is like mapping from just given a set of weights to some prediction about the function that those weights implement.
What is easy then? Like, is it
Yeah.
a constraint that you have in the weights of the model?
So I think all I can really say, we'll say two things. One is I'm going to give some conjectures, some things that I think maybe you can, in a very theoretically clean sense, always be able to do from the weights. And those are both. So the conjecture is about the complexity of the problem given the weights of the model, make some prediction about, or like answer some question about the function those weights implement. And it's not clear if those are ever easy questions. It's quite possible that every question of that form, right, so like the weights could be some obfuscated nonsense. So what am I supposed to do? Yeah, I think yes, we should revisit the notion of what is actually easy in that space. So just to state the goal a little bit, I'm going to sort of breeze through the last 15 minutes, and I'm very happy to talk about all of this in much more detail. This is more like what ARC is up to day right now. Prototypical goal is given the weights of a neural network, given a definition of this function f, given the definition of a distribution d, we would like to understand what is the expected value of this function on this distribution. We want to answer questions like, how correlated is this probe with the truth if I run it on some distribution? And our conjecture is that it is always possible to analyze f mechanistically, to actually reason through the weights in a deductive way, and outperform treating f as a black box and just running a bunch of samples through. So I think this is like a kind of on its face. If you'd asked me 2 years ago, I would have said this seems like a crazy conjecture. There's really no way that should be true. Maybe people think it's a plausible conjecture. I don't know. I'm going to hopefully give some indication of why we feel like this is plausible. Some caveats. One is that in machine learning, I often have the model in front of me, but I care about an input distribution that is defined only by samples. And in those cases, right, we are only going to do inductive reasoning about that data distribution. We're going to have to do normal machine learning about what is going on with the input distribution. What we'd like to do is be able to analyze the part of the behavior that depends on the neural network. We'd like to make inferences because we have the neural network's weights in front of us. So to simplify for the next slides, you could think of the data distribution D as being something which we can write down explicitly in the lab rather than something defined by samples. And we'll maybe return to that later. Another caveat is that if someone gives me an adversarial function f, right, if someone was able to cook up some arbitrary obfuscated circuit and hands it to me, then I think there's nothing you can do that is better than sampling in general. I think under kind of plausible cryptographic assumptions, that's the case. However, the situation we're in machine learning is not that someone handed us some obfuscated neural network. We produce the neural network ourselves by this training process. And so the hope is when the estimation problem we care about comes from a distribution where I get to see the process that actually samples it, then we can outperform sampling all the time. So this point at like the kind of thing that makes the very ambitious goal we're aiming at here, right? If you imagine that you take GPT 5.5 and ask it to play a game of chess against GPT 5.4, GPT 5.5 wins more often than chance. Can you estimate how well GPT 5.5 does at chess by like actually understanding how it plays chess by opening up the heuristics and the planning algorithm and the reasoning it uses in order to play a game of chess, rather than by just playing a ton of games and saying, well, it seems like GPT 5.5 wins more, so I guess something is going on that I don't understand. There's some kind of planning machinery that I don't understand. And the hope is, if you were so good at this kind of mechanistic analysis that you could answer this question by analyzing the weights and actually saying, here's how the planning works, then I'm reasonably optimistic we could answer the kinds of questions we care about for safety. But I would emphasize that is a very ambitious goal, right? The way you would normally answer this question, if you want to estimate how often does it win, is you'd play 1,000 games and look at the win rate. And it is quite bold to say that you can simply look at the weights, reason through the weights. We'll talk a bit more what I mean by reason through the weights, and then make this kind of determination. But that is the goal we're going for here.
This would only be like probably interesting if F is like unbounded, right? Like if F is it being like 0, 1. Right?
I'm most interested in F is 0, 1. So
but like in the like how often it beats it just I could just probably just run samples, right?
yeah, so I'm interested in, can you do a significantly better job than running samples through? It is true we care most about the case. So what are the cases we really care about? We care about cases where the behavior is very rare, right? We care about tail events, which are hard to estimate. Or we care about conditional events, which are very hard to simulate in the lab, which is pretty much some sense equivalent, since you could just probe for the expectations of some conditional. But the conjecture is that this is actually not specific to tail events. It is always the case that sampling was a bad way to estimate things. And even if you have some bounded function and you just care about telling the difference between a 55% and a 54% win rate, we can do that more efficiently by mechanistically estimating or analyzing the model than by just running samples. And again, this is not true if you think of there as being a department that like produces models and then you come in at the end and just get given the model. This is if you get to sit along through training and you get to modify the training process. That's the conjecture. So I will not give a complete explanation of what we believe about this, but I'll try and like sketch some examples, state some conjectures more precisely. So a simple problem would be someone hands you a Boolean circuit and you want to estimate what's the probability that circuit outputs 1 for random inputs. This is a very natural, simple problem. The sampling algorithm is just draw n random samples, run them through, and compute the empirical expectation. What we mean by a mechanistic algorithm as a category is something more like you start with a representation of this known uniformly random input distribution. You somehow like propagate that distribution through the circuit. So you deduce a set of distributional claims about the joint distribution of the wires of the circuit. You end up with some marginal distribution over the output of the circuit, and then you read off that distribution. So instead of propagating through a set of samples through the network, you are making a set of distributional claims about the network that move through it. So an example of an algorithm is, I'm just going to, for each wire, compute the probability that wire is on under some presumption that the wires are independent. And that's like really easy to propagate through, right? I know the expectation of each wire going into my circuit. I can compute the expectation of an output if I know the expectations of the inputs. This is an algorithm which does give me some kind of estimate. It tends to give me a relatively poor estimate, but it does have this flavor of being a mechanistic analysis of what's going on in the circuit, not an inductive inference from a bunch of examples. And I can strengthen this kind of estimate by additionally tracking covariances between different wires. By saying, hey, I'm not going to treat wires as independent, but I'm going to ignore three-way interactions between wires and just look at the pairwise interactions for each pair of wires. And that gives you some formula, like if I want to know the covariance between x1 and x2 with y1 and y2, I can represent that as a sum of a bunch of terms, which is sort of like the structural relationship of how correlations propagate through the network. This is another algorithm which I'm trying to gesture at this like mechanistic flavor of, instead of running samples through and making inference, you're trying to say something about the distribution of the activations of your model and understand how that gives rise to the behavior. So a simple theorem is that if I take a wide random MLP, so I randomly initialize a network, in the theorem statement, I'll have polynomial activation functions that we'll also talk about ReLUs. I can track the first k cumulants in the same time required to run n to the k minus 1 samples through the model. Right, so if I want to track the first cumulants, that's just the same as the time to run a single sample through the model. First 2 cumulants, that's the time to run n samples through the model. Here n is the width of the model. But the error of that is about a factor of n times lower than the error of running n to the k minus 1 samples. So in this case, if the model that I'm working with is random, I can significantly outperform sampling by doing this kind of mechanistic analysis rather than by just running a bunch of samples through the model. This is a graph of what that looks like in practice for a somewhat shallow ReLU network. The black line is the performance of sampling. As you put in more and more compute, you get better and better estimates. The blue dots are the performance of tracking the first k cumulants for various k. And so you get sort of this expected behavior of, you're 10 or 100 times more efficient than sampling when you are able to do this kind of mechanistic analysis. So this is the thing, we're now running a contest of just how well can you solve this estimation problem for random networks. I think our sense is that this problem is very soluble when the input is literally uniformly random. I think our algorithms now are reasonably good, but are not sort of God's algorithms, and we'd like to get better towards like truly nailing and understanding this problem in the simple case where the models you're dealing with are actually random. I think to me it's very interesting, this kind of mechanistic analysis is both very relevant for safety, but very poorly understood even in the simplest cases. And so just trying to get to good on that, trying to have algorithms that work well in simple settings. Yeah.
For this question, for the random case at least, would you be comfortable with algorithms that are of the form, I take a bunch of random networks, I train a network to do this prediction problem and then output whatever that network produced?
I mean, that is very allowed in the competition. The competition is whatever you want to do. Morally, I think we'd hope to have some understanding of how that neural network works, right? In the end of the day, we wanted something that will generalize to new models, and so we're scared of that, but I think it's whatever works. Yeah.
Can you give some sense of why you believe conjecture going beyond like random networks?
Yeah. So roughly speaking, in random networks, what we're doing is we're tracking low-degree polynomials as sort of the sufficient statistics about the network that tell you what's going to happen later. And the reason that works is because random networks sort of obliterate any other information that's not a low-degree polynomial. Right? If you randomly rotate the activations, whatever other complicated thing you're doing is going to get destroyed. So our view is, first we want to understand the mechanics of these algorithms, like how do you propagate features through networks really well, get quite good at that. But the optimistic hope is that the fundamental approach can be very similar for trained models, but instead of the features being low-degree polynomials, the features are themselves going to be learned. So you're going to say that if you want to understand the behavior of GPT-5, and you want to looking at like level 23, the thing in layer 23 that's important is there are features in some sense. There's like statistics of that layer that are governing the behavior, the things that actually matter for what it does. They're just no longer low-degree polynomials. So I'd say it is a big open question whether any of this stuff works as you transfer to learn networks, and that's a huge, huge theory problem.
In that year, what was K?
K was the first K cumulants.
But then, why do you need that for like isn't that like something you choose? Why do you need that for like sampling? Like the number of samples. Why does it appear in the number of samples?
Yeah, so fundamentally what's relevant is this trade-off between how much compute you spend and how good your estimate is. And so you could think of like this track cumulants as like a series of algorithms for different values of K, and sampling is a series of algorithms for different numbers of samples. And so we're just comparing between, as you vary the number of samples in sampling, you get this black line for every possible value.
If I fix the number of samples, it would be that divided by n.
Yeah. And again, it's like a little bit cheatsy because actually I do better at powers of n, right? It's just easier to analyze the behavior of neural networks. You can beat sampling by more when your number of samples is an integer power of the width, but we could talk about why that is. Actually, I think we probably can't talk about why that is. I'm going to take like another 3 minutes, just go through one formal conjecture and then wrap up. Okay, so a conjecture I believe in that's fairly bold. I think it's not clear if this gets you to trained models, but I think as a theory statement is an extremely interesting statement, and I think it actually is closer than it looks to the setting for trained models, is that for every distribution over estimation problems, there is a mechanistic estimate that significantly outperforms sampling. A reason this is closely connected is training is itself just another distribution over estimation problems, right? It's a very complicated one, but you can work up the complexity of these distributions over time. So if you imagine I specify some function family, right? So some f, it takes as input theta, which you should think of as the weights of a neural network, and x, which you should think of as a random input to a neural network. That runs in time t. And if you give me an estimator, which runs in time k times t, which tries to predict what is the expected value over a random x of that network, we can define the mean squared error as just what is the expectation over the random parameters of a network of the error between our estimate and the expectation over a random input x. This is saying how well do you characterize the performance of this neural network for a randomly chosen network. Right? The error of sampling decays like 1 over k. In a very straightforward way, for every estimation problem, if the mean is 0 and the values are plus minus 1, or get about 1 over k. There's a conjecture that for every single distribution over estimation problems, you can always outperform that basically by a logarithmic factor. It is never the case that sampling is optimal. So there can be, in some sense, at most one value of k for which sampling is optimal, but if that's the case, then error must decay to 0 shortly after that scale, and it must have actually been small even at smaller numbers of sample counts. So why this is interesting to us And we're interested in exploring mechanistic algorithms that take as input the weights of models and make predictions about their behavior. I think a very natural concern to have is that sampling kind of is a really important technique for doing that. And the conjecture is that's actually not the case. That is an algorithmic limitation. And this is potentially a very simple theorem statement that captures, or conjecture statement, that captures a way in which sampling is suboptimal. And if we really understood this kind of issue, if we got quite good at this business of making predictions about functions from looking at their implementations, that would be a very powerful step towards making predictions about learned neural networks. So excited to talk about any of this with folks over the rest of the day. But thanks for the questions, and great talking to everyone.
We have time for maybe one quick question before the next speaker steps up.
Yeah, thanks for the great talk. I wanted to disambiguate two versions of like non-adversarial functions that I thought I heard. One of them is where we have just had a standard learning algorithm, but we get to see the weights. The other one is where we maybe like ensure the learning algorithm is honest or aligned with us somehow. For this conjecture, which version of non-adversarial?
So for this conjecture, non-adversarial is captured by the fact that for every distribution over problems, there is an algorithm. So if something funky is going on in the distribution, then your algorithm potentially needs to get that advice, right? Your algorithm needs to be adapted around that. But if you define any learning algorithm where it's transparent to you and you get to see that, so conjecture doesn't fully cover everything you might want from a learning perspective, but roughly non-adversarial is captured by saying it works for every distribution over estimation problems. I think that's like a really important part of how you move from the worst case setting where I think you actually can't do better than sampling. Like the fundamental move is saying we want to do well for any distribution, including very rich, complicated distributions coming out of training on complicated tasks.
So there's like, if there's some obfuscation strategy that's actually being integrated into the particular estimation algorithm.
Yeah, so if the important point is that you get to see, if it's this training process, you get to see the training process. So you can't like do obfuscation during training. And if the estimation problem itself, if the distribution bakes in some obfuscation thing, then the quantifier order is very important. That we say for every distribution, there is an estimation algorithm. Great, thank you again.
Yeah, let's thank the speaker.